My name is Krupa Galiya, and so warm welcome everyone. Thanks for the joining. It's Monday. So title for today's session is the introduction in the hands-on workshop with the reinforcement learning. And this is the main agenda that we are going to cover. So we'll start with the first, just explaining, just understanding what is the reinforcement learning. We know supervised and unsupervised learning. So how it differ from unsupervised and supervised learning. We also see the real life example that we actually used to have in real life, but we don't know that's actually reinforcement learning. And then we will see what is agent and environment, how they interact in the environment, and then like how you can formulate any problem to the reinforcement learning. So not all problem can be solved by reinforcement learning, but you can kind of get an idea of what should be the approach or what kind of the elements you need to take care about when you start with formulating problems that can be solved with the reinforcement learning. And then we see open source reinforcement learning libraries. There are few that is of course available in the Python. You can of course look into GitHub and look more into it. And then from the 5th, we start the Google Colab environment. So up to 1.24 we'll be having in this slide. And on the 5th one, we solve one like a reinforcement learning problem with 2 algorithms. And we also see one of the algorithms in the theoretically. So 2 algorithms we'll see in the practical. And we also see how the gym library is useful in here, like how we can create environments with the gym library. And then on the last, we also see the use cases and the reinforcement learning resources to get started. This is just introductions or and few algorithms, but there is definitely a lot more coming up in the research area in the reinforcement learning as well as the real life applications. So there is a pretty good, interesting learning resources as well that you can explore more. So let's start. So first, we know supervised. So supervised, we mean by we have the labeled data set, and we tend to solve problem like object recognition kind of thing. So we have regression classification kind of thing. We of course have a label data we call as a exit value, or at the training we call as a ground truth. And we do training with some supervised. Supervised mean we have the label data. While in the case of unsupervised, we don't have any label data. So that's where it learns the patterns from the given data. And that's where we say our clustering algorithm and the association algorithms. We don't have any supervisor here because data just learn by exploring the patterns in the data. And we don't have here any labeled data. So it understands from the pattern and then discover the output. So it should be cluster of grouping the same kind of entity that has the same kind of features. While in the reinforcement learning, here we have the agent, and the agent interacts with the environment and it performs certain actions, and it basically learns from trial and error. I try something, but that didn't work. Then I try again. Okay, that works. So that is how the reinforcement learning works. Here the agent is the main, the main persons who does the all actions based on the state. And then here the problems we saw as a reward based, consider any game example. We do something, we for example in the game of some Jungle Mario or such kind of game, if we don't if we take such a coin, or if that Mario hit any coin, then we got some rewards, we got some points. So that's type of the problem that is in the reinforcement learning. And here the of course no any supervision thing. It just learn from exploring the environment. And then it of course have some policy and all. So we'll see that in the deeper. But the main idea here is just follow trial and error methods in the reinforcement learning, while this supervised and unsupervised is the different approach. So we know this both thing, and now I hope we have just little bit idea about reinforcement learning. And now we see deeper in the reinforcement learning. So that's how the this 3 kind of learning there's available in the machine learning. We mainly heard about supervised and unsupervised, but reinforcement learning is the third one. So let's just try to understand the reinforcement learning by some simple example. So let's say here, this is like, this box, that rectangle box that we see is our environment. And this robot we see, so that's like agent. So the being person who does the all activity in the environment, like everything happens in the environment. And then there is like two things here. So one side is fire, and the another side there is tap, and there is bucket. But bucket is not like directly like exactly close uh in the near to the tap. So like water is just dropping down. So first action of the agent is just like, observe the situations or the environment, and then it selects the action using some policy. But for now, the robot is pretty new in the environment. Robot don't know anything. So robot just hit to the fire, and then he got like, some punishment. So we can say the marks or like rewards is being cut down. So that robot got minus 50 point. So based on that action, like robot move from center to near to fire, it just decreased the point. So that's we call as a like, penalty. If it goes to near the bucket, and if have like, the bucket should be in proper directions, if robot did the task, then we see is like, rewards, like positive rewards, we got some more score. And now as the robot hit the fire, so now robot say, okay, so fire means bad, so next time I definitely avoid the fire. And that's what it learns. So that's it updates like, policy. Okay, I learned like, fire is bad, and then it will iterate up to finding the optimal policy. And then like, the robot will learn everything in this given environment. So robot stays like agent or robot in this case just stays in this environment, and it learn in that one. Let's see some live real world like practical example too. So for example, you have dog and you are trying to teach a dog like how to give a handshake or just how to stand. So here we consider like full environment is your home, because you do that activity in your home. The agent, the main entity who does all the tasks, that's the dog. And then action is the muscle contraction. So like, dog like move to like, upward, downward. He does some things. Dog actually don't understand our language. So like, we don't know, like, dog don't know like what exactly behave. But when dog does something that we like, then we give reward as a food, like, as you see in this picture. So then the dog is like, okay, to get the food, I need to do this. So that's like positive behavior. If dog does something like, if the task is about, let's say, handshaking, but the dog didn't like able to do that because dog understood something else. So and then we don't give a food or like any snacks. So that's how the like, dog learns. So dog like now it learns, okay, if I do handshake, then I'll got rewards. And reward is like, I got food if I do handshake. So that's how the dog learn in this like, environment. And this is the some another example. This is also like how we learn to walk when we are like baby. So that's we say like environment is like, sofa, the floor, or let's say in the home. And here the child is the agent because that perform the activity, because he trying to check the uh, do the activity of walking. And then the action. So what kind of action this baby can take? So baby don't know how to walk. It's like pretty difficult for them to walk as a start when it's like, 6 to 12 months in that period. So they do action like that. First try to balance their body, step a foot ahead, and then they observe. So what's their observation? So they observe other, seeing like, how other walks. And like in like, first they know if I have like, if I say, for example, if I have my feet on the proper position, then I don't fall. And then as a reward, like, his or her mom, so like, dad claps, and also they'll like laugh. And so that's how the baby know, like, I did something great. So that's why they all are happy. And the same thing can be applied as when we learn first as a bicycle. We done something and then we fall. So we know we need to like, adjust the like, balance of the bicycle. And then that's how, because we in this like environment, or maybe let's say environment is your garden or some playground area where you are trying to learn your bicycles. And then we learn by that one. If we fall, then we know, okay, we don't need to do that. If we have certain actions, like if we properly balance our bicycle and our body weights in the proper direction, then we can able to move to the far place. And of course, reward is we got learned to have bicycle, and then we can like go in any like distance in the short times. That's how exactly the same approach can be actually is being used in the making humanoid, like human robot, and they make it walk. So it also does this. It also follows the same one, human robot. So it learns from the environment. It observes the other one. It has like lots of trial and error, but then eventually, based on some of the observations and the actions that humanoid or baby or like any person takes, then it finally got to learn. So that was all the example that we are seeing. Now we can see the like typical definitions or in the more like kind of in the technical term. So reinforcement learning typically referred as an agent. So that person like robot or baby interacting with the unknown environment. So that's not known. There's like it's all like new. So it's like unknown environment. So same like if you are trying to like learn a bicycle, then it's like totally new environment and everything is new for you. And then here the main important thing is the sequentially. So here if you based on the like agent learn from the environment sequentially through actions and feedback it gets. So feedback would be if the baby is like able to exactly balance the properly, then it gets like positive feedback. So rewards the like claps. So it's like sequentially. So you move one step and then second step. So it's like sequential, and then you just baby just walk 4 or 5 steps. And then the main superpower is like it don't require labeled training data, and it makes a short-term decisions. Can make short-term decision while optimizing for the long term. So optimization is also one interesting term here, because we try to optimize the maximum rewards in our case. And here time plays, of course, crucial role in the reinforcement learning. Like it should not be like too much longer. Like the agent is still trying to learn, like like baby is still trying to learn, like even after let's say 2 years. So it's like time also plays important role in the reinforcement learning, even in the programs and the algorithms that we see in the later part of this session. And of course, there is no any supervisor. We just have the real number and the reward signals. And here our goal is to maximize a future cumulative reward. So it's just not one step. At the one step, you got the maximum, so you are done. But you need to reach to the goal by taking the maximum best possible steps, and then you can maximize the all future cumulative rewards. So maximizing and the future cumulative rewards is also important, that we all going to see all this theoretical approach in the coding session when we do hands-on. And this is the agent and the environment. So we seen little bit before of this, what is agent and environment. So let's say agent and environment. So like agent, of course, does some activities or certain actions, and the environment has some state. So for example, here is the agent, and given at the state, it takes some actions in the environment. And then environment has some updated state, like, so previously someone does on something like, like for example, someone changed your book or something. So that's like updated stage. So that's updated state that you got from the environment. And then reward, it can be reward, positive reward, so it can be a negative rewards. So that's agent research. So these cycles, like, how agent interact with the environment and try to make the smarter decisions to maximize the cumulative rewards is really important. And this graph is like, basic one, you can say, about the agent and environment, how they interact, how the agent interact in the environment. So hope up to now we got little bit idea about what is reinforcement learning. Does anyone have any questions or doubts or anything? They can of course post to in the chat here. So now we have understood, like, what's the reinforcement learning in the nutshell, and in some of the details with the examples. And now we see how we can formulate the reinforcement learning problem. It's all based on whatever we see previously. So we have the environment here. So that's why, like, physical word. If it like, game, so it's like, game, math or something. So that's like game word. So environment is like physical words in which the agent operates, like, it does certain action. A state means current situation of the agent. For example, if we take one example here as a chess game, so environment is like, all that, the matrix of the chessboard that we have. So it's like environment. And state is like, you have bishop here, you have horse here. So it's like, the state, that current state, if it like it, so that's current state of the agent, like the whatever they perform the activity. And actions, so it will be activity, like, perform the possible moves that the agent can take. And rewards is like, positive feedback, more score, or if you just take any of the, like, pawns from the opponent's participants, so that's like reward, you got some more positive scores. And here the word is policy, which is new. So policy means it actually is like, kind of a methods, or you can say algorithms, that map agent's current activity, agent stage to activity. So it's basically a strategy that applied, that of course, like, whatever the action in here takes is taken by the agent. So agent takes the some action and then decide what, based on current one, which next activity should the agent take. So that is like, that's like how from one step you move to some another stage. So that is like, you have some learning mechanism in that one. And that's we call like, a policy, which basically in the simple word, it just map agent state to the action. And value is like, future reward. For example, if I perform from here to this step, what will be the future rewards that agent can take by performing certain activities in the particular stage. So that's like, six basic ideas or the elements in the reinforcement learning. And now we have one environment here. So can we please guess, like, what is what would be the environment, like whatever we see here in this one, what will be the environment, what is the agent, and the, like, rewards or the punishment in this like Pac-Man game. It's like Pac-Man game, kind of well-known game, this one. So I got one question. So what is different between action and policy? So action we mean by we do some such kind of activity, or like, positive all possible moves. For example, if we take a chess as example, so we have like, so for example, it's like 8x8 or like 16x16. I haven't played chess a time ago, so I kind of forgot. But you have like, such kind of matrix in that one. So in that one, you have all the possible activities you can perform. You can go like, one forward, if it like, pawn, and like you go in the, like, upside horse, just like, 2.5 points. So that's like all is like action. And the policy is one kind of algorithms that actually says if this action is helpful or not. So that's what actually the policy is. The policies is like one algorithm, or like, for example, if you know this game chess, so then it means by, the policy of the chess, like, kind of the what you need to do, because you have played it so many years, so you are kind of good at it one. So it's like different. And also we see these examples and everything more in the hands-on session where we see, but that is like, basic idea between actions, possible moves, possible activities, and the policy is like, state to action. So if it like helpful or not. So that's why we have some strategies, some rules or some algorithms in that one. Cool. So now, yeah, back to this one. Guess the element. Okay, so game area is the environment. So that's perfectly right. And the score is the reward. Yeah, so we see here the score, and like, as the Pac-Man is eating all this, like, white dots. So that's how it's getting lots and lots more and more scores. And what is the punishment in this case? So we got reward, we got the environment. So yeah, environment, Sai Manideep is wrote, environment is like, enter map. Action is like keep moving to hit more points. So yeah, so that's activity or like action. So it could can go into like 4 directions: upward, downward, left, right. And the reward is the score. That's perfectly right. You got it. And what could be the penalty in this one? So the penalty is, for example, if all this ghost that we see in the this, they are changing the color right now, it's blue and then orange. So if we got hit, if this agent, which is this green one, got hit by that ghost, then we lost the game. There is no any points and nothing. So then that's the penalty. So that's why if we train a reinforcement learning on this game, so now that green one, the yellow one is the agent, and then it learns, okay, I should not go near to that ghost one, which is white one and the orange one, and then I should always follow in the direction. So that's action. So trying to get the maximum score. So that's by eating all these white scores or like coins or somewhat we see. And also if they eat this ghost, then it's also getting more scores. So that's how if you try to train a reinforcement learning algorithm. So on this one, on the Pac-Man game, then it learns all this thing, and then it in just few times. So when you start with algorithm, so in that way, just like try making random thing, it will get, of course, lost so many times, but eventually once it's learn to play this game, it will run even better than a human. So that's how the basic idea of the reinforcement learning. Okay, yeah, I see lots of replies in the chat. So yeah, hit by ghost is like a penalty one, that's right. Cool. So now we are moving toward with hands-on and the implementation parts here. So there are like 4 or 5 libraries that we have listed here. So it's like kind of the basic one. You can of course use the different libraries too, but that's how they have it's pretty good in the production environment, or maybe lots of people use it. So that's why it's in this list. I haven't tried all these libraries by myself. I tried few of them, of course, but it all has different varieties and the features of it. So the first one, let's say, is the reinforcement learning. So here in this library is like pretty easy to interact with the TensorFlow. You can also easily all the functions and everything, and you can also pretty easily make the reinforcement learning models too. If we see this one, which is the AI baseline, so it's high quality. It's from the OpenAI, so it has so Gym is also from the OpenAI, but in this one, it has some higher quality of the implementation, which is more precise. It of course from the OpenAI, and where you see it's DQN, which is deep Q network, kind of, you can say another level of the higher level, you can say, of the libraries. And then this is also good one. It is specifically used for the if you want to build in the application, even though they have lots of tutorials and the videos too for this one, which is like Ray, it called as a Ray. And then not just only reinforcement learning, but it is also used for some another normal ML kind of applications too. And then the state baseline. So we have like scikit-learn normally in the ML thing. We have supervised and supervised scikit-learn, like random forest kind of thing. So in that one, you just got functions in that one, and then you just start implementing it. You just passed a few parameters in that one, so you don't need to build from the scratch in that one. So that's how the stable baseline libraries is it. So yeah, and I got one question. Okay. Okay, so that's overall basic one. We're going to see. So that's like implementation of the algorithms. And now we are moving forward with our hands-on collab session. And before we go there, does anyone have any questions or anything? Okay, which library is the best one and why you think so? Okay, great. So I think each library has its own benefit or anything. So personally, when I tried this table baseline, so it has a good, I can pretty quickly get the model, and it's quickly running and everything. So it's more for the production kind of pipeline. But when I see the this Ray library, so in that one, if I want to do some more research on some algorithms, I seen lots of people refer in the research paper too. So that's how, like, and if you have, like, so like there is PyTorch and TensorFlow based environment too. But yeah, I found like Berkeley's Ray library as well as stable baseline. Stable baseline when you want to have some applications live and you don't want just like, kind of industrial kind of thing where you just directly get some algorithms or maybe fine tune it sometimes without worrying too much about the, like, all the, like, lots of dependencies and everything. And it's like PyTorch based, you can of course change the parameter, hyperparameter, tune it a while, and you don't also need to have implementation of, for example, DQ1 by full end to end with, like, using, for example, let's say TensorFlow, Keras, and all things. So stable is kind of a wrapper around it. So yeah. And also I got one question, how to improve skills in the reinforcement learning after learning the basic one, get better of using for different problem. So that's where we have the RL resources, how put it together, like, after researching a lot. So we'll see that at the end of the session, but yeah, we are definitely going to cover that too. Cool. So now let's go to the hands-on. Let me turn off the extra one. And you can also do a live with me. You just need to copy this link here, which is the bit.ly.3GVVOT4. And you just need to type this down in your browser and just make sure you are logged in the Google. Like, it's like, for example, Google account. And then you will see such environment here. And before going to do anything, okay, let me have this link in the chat section. Okay, so I pasted the link in the chat section. And if we go to this link here, so first you will see here one option too. I don't see because that's my account and I have created that one. So you will see copy to drive. If you don't see here, then I suggest please go to file and save a copy in drive. And that's how the this same kind of environment would open. Save a copy in drive, because right now it's like, everything on the Google Colab server in your case. And then if you make any changes or anything, you can't get able to access that changes later on. So first I suggest to go to here and click on save a copy in drive. And if you click on that one, it will say creating a copy. And then you got some pop-up thing you can do in the desktop. I think in mobile, I'm not sure if possible or not. And then you will have, if you click on open new tab, and then it will have the same exact copy. So now you have that saved copy in your drive. So it's saved here, like such kind of thing, like last save or something. But yeah, that's how you can get your own copy. And those for those who are not familiar with this environment, so just a 2-minute introduction for those people. So it's Google Colab environment. Why we are using it? Because in that one we don't need to tackle, for example, I use Mac, some use Linux, some people use Windows. So everyone has, like, different environment and lots of different kind of dependencies too. But here we just have one environment which is based on the like Unix based OS. And then if I type something, if I use something, then it will be also going to save for your too, because we are in the same environment. And it is of course pretty easy to share, like just how I shared with you. And also you can easily connect with a drive here, Google Drive. Right now I haven't connected because we don't need in this one. We can also get access of GPU, TPU and everything. But yeah, that's basic one about the Google Colab for those who don't know. But here is the, like, Python kind of Jupyter notebook environment. So here we got the text as well as the code. Cool. So enough for the Google Colab introductions. So now we see, if you don't see here the connected, right now for me is connected. But if you don't see or is not connected, then I'll suggest please click on here and, like, connect. Like there will be button called connect. So you can just click on connect, and after in just 1 minute you got connected, and you will also get this kind of same symbol here. Cool. So now we first so this is our table of content for the Colab. So first we'll we'll do lots of installations and visualization related libraries. So we can move further in this one. And then we explore what is gym and the gym environment. So gym is libraries. So we're also going to see that one, what is this does and why we are using it. And there is also lots of environment. We're going to see that one on the live. And there is one problem, which is frozen lag. So we just selected one environment or one problem, and on that problem we are going to have a reinforcement learning algorithm. For example, q learning, epsilon greedy algorithm strategy. So we are going to implement this both thing on this frozen lag problem. So like this one environmental problem, whatever you say. So we are going to see that one with this one q learning and epsilon algorithms, and then how this two is different. And there is also one another techniques, or the neural network based methods, which called as a deep q network. This thing is extra if we got more time. It is more about how you can save, we save load after we done with training, we save our model, and then we load as predictions. So how we can do that same thing with reinforcement learning models with using this library called the stable baseline 3. So this is optional. If we got time, then we'll see it as this link, and everything is available with you. So you can also explore that one. But this is main topics for today for the hands-on. So first, I suggest this code, and there is text also. If you click on here and then click on here, so it will run this environment. For me is already I run and I install everything, so I don't need to do that. But for you need to click on, or you can also click on getting shift or return, or enter in your case. And then this one, so this one basically installed OpenGL and all is the graphics library, because here in the Colab we don't have graphics supported and everything is a by default, so we need to install that one. There is also Pi virtual display, so in that one you can see the environment in the virtual display. So it's this too is requirement is for the visualization purpose. It is not related to with the reinforcement learning thing. This one is the gym. So gym is the it's developed by the OpenAI. So it's toolkit for developing, comparing the reinforcement learning algorithms. It's not just used for reinforcement learning algorithm, but it also gives lots of the standard environment too. And what are those environments that we also going to see that. And here I have installed everything. So you can also do this one by clicking on here. So it will install all the components of the gym. So all the environments that is available in the gym. And then you may got here, so you can click on restart. And once you click on here, you can just directly move to in this part. So now up to here, we just installed everything with the pip and apt-get, and here we start importing whatever we need for. So gym, of course we need, NumPy is of course we need, and the matplotlib for the plotting, and Python display. So that's how we see environment in Google Colab. So we can click on, for example, here running, and then from Python display, we say just here we are defining the size of the display. And then we are mainly done with the importation and everything. Now we have everything we did, everything is ready. Now we just have to cook. So here, let's explore the gym environment. So before we are going to further in this code, let me open this one, which is the gym environment. And here you see all these different environments available here. So this one is for the Atari, for all the game. It has a lots of things actually. Yeah, so all this, most of I think games could be familiar. But in this case, it will be the whatever agent, or that it will be learn to play the game in this environment. For example, it's cruel or kangaroo. So here the agent will be whatever, maybe it's kangaroo. Then it will try to learn and get the maximum rewards in this game. And this one is also pretty interesting, which is mainly used in the making humanoid or maybe some industrial controls, industrial applications, or such kind of maybe self-driving car as well, like inverting pendule or something. Uh, so maybe you have seen such pictures before, but it's here it's about like multi-joint dynamics with the contract. So like it's just not like one thing. For example, here you see, and then how it like trying to walk and how cheetah. So that's our goal. So first the ant or like cheetahs don't know how to walk. This humanoid like it's just like falling. And then here the humanoid is like just like sleeping. Our goal is to make it a stand. So like we are trying to get a humanoid to like so it's like stand well. And the toy text. So here we have some blackjack, taxi, or cliff walking, frozen like this. What we are going to see in the deeper. And the classic control is that's where the like pendulum or mountain car. So you can of course like go deeper in all of these. And this third party environment is also interesting. So let's say this one, Flappy environment or a volleyball game. This is like, some of the like, person made this GitHub repo and then they made open source and then they are highlighted on the OpenAI website. So it's about that one. You can of course make your own custom environment as well, and you can also publish it. There is a tutorials as well, I think. Flappy Bird, or say like this volleyball. So like so in here there is two agent, and this two agent is like like for example, two robots is playing a game with like ball. So this like and it's like created by some author and everything. So yeah, that's all the like environments, and we are going to load this environment in our collab. So that was whatever we see. So that was chiefs of all this. But here we are going to, for example, it's pretty easy in the gym to select any environment and get started with it. So first, we selected the environment. For example, I'll say cart pole, which looks actually like this one. And this is just a version. So I'll say, I want to select this environment. So first I reset. Just like reset is like, just before starting anything, any interaction with the environment, we first need to reset it. And this is rendering. It needed for, because we are using Google Colab. If you use any like local system, so in that one, you don't need to write this code, but this is just rendering purpose. Like, I just get the view for that one as a first screen. And then I'll say, perform some action. What action we're going to say? Perform some action 50 times. So we have here loop here, and then we are selecting some random action. So environment is taking random action, and this line, like environment, so like this syntax or line is about taking the random action by the agent in the environment. So in this case, this is agent and this is like environment. So it just move to like the goal is to have it like steady. This gray color, so it should be like steady one, because right now it's like moving. When we also in, it will be moving, but our goal to have it like very steady. But right now we are just like visualizing all this, so we can just see, have the any random action and random action. So it's just random. The agent don't know what to do or not, so it just like move here and there in the environment. Basically, that's what this line does. So we call as a select a random action. So action is meant like possible moves, as we seen before, possible moves in the environment. And then here we take action. So step means action that we take. And steps actually gives 4 things to us. So one is like observations, and the rewards. Is it going positive, negative? Because after we done something, we need to know like what is the effect of that one in the environment. And done is like so if it done, like is it steady or is it just falling all the way down, just fall all over on the like horizontal line. And then info is just used for the debugging purpose. And then we take here step, and then This part is for the visualizations. So after agent taken some random action, what happens? Like, so we want to see that one. So that's why we say here, like, whatever the current stage of the environment is after taking a step. So then we do render. So it means present or show me that action. And this for the visualization, which is just show and display the clear output and display. And if it done, so break the loop means if this agent is like, steady or exactly what we do, then just stop it. And this is just to clear. So if we run, you see it's moving a very bit because it's just one step, but it's moving if you have noted. It just completed the 50 50 times. So like you can say loop went for the 50 times, so it moved for the 50 time, but it just moved not too much, but a little bit. And the same thing we have this year with the mountain car. So we have taken the 0th versions. And if you see, so here the goal is to, this is the car, and it should not go like, after this direction, like, not too much on the left side, just like, out of the environment. So that's like end of the environment. And this here, the flag, we see our goal is to reach this car to have this one. So right now it's just like, just playing randomly. So, it's moving just random, like forward, backward. So here the action is like, to forward, backward. And then it also has like, brake control and everything. Whatever the other actions needed to drive the car. And this is also interesting. So it's like, kind of a humanoid or the bipedal walker. And it has this route. This is like, starting one. And we need, our goal is to like, so this agent should able to learn walk in this environment. So it should not fall into this cliff, this one here, and it should step above when it has like, because it's like kind of forward direction in here. So right now it's just like all the things that we see here, it's just like randomly taking a move. Now we are very curious to see how we can able to make this like, learn, because like, right now, like randomly, we don't like too much random thing, but we want exactly. So our agent should be exactly learned well. Okay, the above one is still running. Okay, so this is how it learns, kind of like not learns, walks just randomly. In your case, when you try, so it will be maybe like different one. This car racing is another one. There is actually lots of the environments. I think all this list I have, so you can just, so if you see all this code here, so I haven't done anything. I just changed this one. This domain randomize, it's just optional parameter, needed or not needed. If you just have this environment, like, gym make environment, so it is making environment. And then all other things, it's just the same. The same you can explore with all these environments. There is also environment like Atari kind of environment where it needs some extra graphics libraries, so that need to install, but it has a lots of environments. And now we dive deeper in the frozen leg problem. So this problem is here that we just seen before, but not too much in the detail. So it looks something like this. So here is our start, here is our end, on the bottom right, and on the top left, here is the agent, or like, this one, like moving. And all this area that we see in the white, so it's like frozen lake. And when we see this one, like green, blue one, so it's like, a hole. So that's why if that agent fall into this one, so it like, just lost the game. Negative reward, we don't want that. We, of course, our goal is to reach this agent to here. And right now, as we seen in all the environment before, and the algorithms and all that we are saying, it will be also same for all the other environments, like, the robot walking, or maybe that car one, it will be same, but it's just that I have taken this example. So it's kind of like, pretty easy to explain. So that's why I have taken this example, but it's just like, one line of change, or maybe they have some different actions and everything, but that is pretty configurable. So it is easy to try this algorithm that I have shown you here with this one. So first we are taking this frozen lake. Slippery is like, when let me first run it. So when the agent is on the on the a perfect area. So in that one, it could be a sleepy. So it means it could fall into not be rewarded by that situations. So if you see in that example that I just shown, so it was like the robot was making some room, some move to right, then back to that position, just random, don't know what to do, and then back, and then it finally fall in this hole. So here our reward is, so reach goal means here where we see the box. So we have our gift here. So if we reach to this one, then we say we got 1 point, and that's what this agent or we won the game. And if we fall to the hole, then no any point 0, and the frozen. So frozen means if you are staying at this situations, so we also don't want that. So there is no any rewards or a positive point for that one. And then if you have noticed, there are different 4 kind of action in this one. So the robot could be go left, right, down, and upside. And I have denoted one code here like 0, 1, 2, 3, 4, 1, 2, 3. So it means like, if you remember this line before, so it was for the environment. In environment, agent can take any random action. So for example, here it's 1. So it means like, so from here agent is just like, going to down. So it's 1. And then here I'm just using full form like environment instead of env. And then observation space, this is important one to move forward, because here we are taking the like kind of the inputs from our problem. So observation space. So we see here the grid, which is 4 by 4. Each has some features, or like some may have frozen legs, some may have hole. So here we say our like, all the possible moves or the actions of the observation could be this 4 by 4, which would be like, 16. And the action that we see here, the agent can perform only 4 actions. So that's why we got this 16 and the 4 here. And now this part is basically start the Q learning. So it's like one of the most popular reinforcement learning algorithms, where here we try to get the value of Q. And Q is like, what's Q means? The Q is the quality of certain action in the given state. And it based on this function, like, for example, Q. So S is the state, A is the actions, and it predicts the functions, which is the best action in order to have a maximum reward. Because in this one, we want to, of course, our goal is to get a +1. And that's why we have this one. And so we'll do this iteratively, like, as I mentioned before, trial and error kind of thing, using the Bellman equation, which is also one equation. Most of you already maybe know this before in the study. And then, so Q is, as mentioned, is like quality. And here with the Q learning, we build a Q table. And Q table would have the row and column, like every table has a row and column. And the row would be all the states we have. And the column would be the action. So we have S is 16, because we have total states is like 4 by 4, so it's 16. And A is the action. So we have 4 action in this one. So based on this one, we are going to basically implement this Bellman equation in the like Q learning form. And then this is just overall brief flow chart for the Q learning. So we first initialize Q table, then we choose action, perform action. Based on chosen action, we perform the action, measure rewards, and then update the Q. And here, so as with any ML algorithm, we first start by training the algorithms. So first, we define our like, table. So I'll say table, the size of the table. So I first, as like, it's just first time. So I'll have all the table, all the like, Q table variable would be 0, 0, because that's how I'm initializing. An episode means like, full cycles. And full cycle, I mean by agent start from the start position, and then it learns everything, or it may reach to the goal, it may to the fall onto the hole. And this is the alpha, means learning rate, which always 0 to 1. So it like, kind of have this balanced between the new knowledge and the past knowledge. And the gamma is a discount factor in this, like we say, as a like discount factor. So it like, care about the future related. So like the more is like, if 0 to 1, the range is, and if it has a more near to 1 value, so it means we are more focused on the long-term goal instead of short-term. And this is the list of outcome to plot. So like we'll see this one later on, how we are using this one. So I'm just printing here Q table. So we know the value would be 0, 0, and the size would be the 16 by 4, 16 row and the 4. And here we start with all the 1000 iterations of the episodes. And as we did before, we first reset the environment before doing anything. And here the done means first means we are not done now. We just started. So at the start, the agent is at the start positions. And as the start positions, it's not success, it's failure. So it's like default one, we say as a fail. We have set this two variable as a default one, because that's going to change later on this part. And then say we are going to repeat until there can be two situations. So one is stuck in the hole, that's the end of the game, and the other one it reaches to the goals. And so we'll keep training it up to this iteration. So for one iteration, while it's not done, we choose the actions with the higher value in the current stage. So we see if the Q table of that stage has some value, because right now it's like all 0, 0. But if it has some value at reaching some particular stage, so if already Q table has that value, so we can of course use that value, get the index of that value. So that's what the np-argmax function does that, and then we take that actions. We consider that actions. And if we don't have value, then we just need to have the random one, just choose anything, because there is no best action. The Q table is just all 0, 0. And then here we take step. So we take actions and move agent in that one. So action we got. So one could be from the Q table, one could be the random one. And then we have taken this one, which is the syntax of step functions, means taking steps. And then we got this whole thing here as we had the before. And this is where that previous equation that we see. So it's like modifications of that equation, which we call as strategy for updating Q. So that's what we call Q learning, like quality of the values. So here we have, and this will basically, so this equation basically update the value. And here if you see, it just basically consider the rewards between current one or what could be the future reward on that one. So in that one, for example, I got this reward here. Alpha is our learning rate, gamma is our discount rate. So because we mainly focused on the long-term goal, and then based on equations, getting the maximum value of those stage and getting the index of that one, we update the current state. So new state become the current state. And if we got the reward, so if this reward is 1, positive 1, then we say the last outcome that we set as a success, the outcome that we set previously as a failure should be the success. And then I'm just printing here. So if I just run this quickly, so before training, so 16 by 4, and then after Q table learning, we got some values here. And this is the graph that I used to the outcome, which has basically two values, failure and success. As a start, the agent or whatever that player was, so don't know what to do. So it was just always failing. But here after actually, I think 150 iteration, it's just always learning a well. Maybe we can also just stop at the 202. That's also possible, because this one is always going to success in this one. And then here we just kind of evaluation method we did. So here we are basically choosing the value from the Q table, because Q table is updated and ready. We just have to take the value from the Q table and perform the action on that one. If no, not value present, then we just have the random action here. And then we take one steps and then update current one. And then this is just, we are just adding to the NB success, because then we can see the average success rate, which is okay, 100% success rate. We can also see that same thing from this graph. And then this is the visualizations. So using that Q table, so if you see, for example, this agent moved here. And if you say I'm also printing some values down here, so it will say the directions maybe in your case, it will be, and it will learn in this direction too, like, down, down, and that one. And then this is like, the values that we got. For example, the action it takes, so like, 2, so 2, if you see above, so 2, 2 is like, right, right, and 1, 1 is like, down, and then 2 is again the right, because we have reached here, so here. And this is the Q table, just printing here uh for the just reference. And this is the second algorithms. We have some this is very similar as the Q learning, but here the thing is epsilon algorithms just find the good trade-off between the exploitation and the exploration. So exploration we mean by, in the previous, when we don't have any value present, then we just take a random action, a random one. And when we have the value present, then we of course choose that value. So that's exploitation. We always focus on the higher one and we just select it. But that could be some another cases where we can get the stages or the values that is better than what we have the currently. So that's the kind of the drawback you can say for the Q learning. And that's for this epsilon greedy algorithm. And this algorithm is also one of the base for the deep Q network algorithms. And if you see the code and everything, it's just almost the same. Here we have the 2 parameter, which is this epsilon and the epsilon decay. So it's just like, at the starting, we have the 1, and then iteratively, we will going to decrease this value. So if you see here, the only part change here is this one. So first, it takes like, just like any random number. And this one gives a random number between 0 to 1. We have already imported the random. And then epsilon is, of course, like, as a first, it's very great. So as a first, we take the exploration because like, it's just new environment. So we try to have a more and more exploration. But in the previous case, once we got the higher value, then we will kind of stop. But here, based on some random thing here, we are going some more chances to age and to explore more things. So you should not be just like stable, but the environment is like, no, right now, all the age cases. And then if this like, if it like R&D is like, very small, then we just select whatever we had in the Q table. These all same, this equation and everything. Once we run, then we'll see the different actually. So if you notice, so this one as before the Q learning table, and this one is after the Q learning. So if you see, this has the more values compared to before, because it not just only learn in like, 1 or 2 direction, but it now explored a lots of the points, and it's like not like, kind of stable in that way. It's like more flexible because it's not lots of the step to it. Also taking a time to, if you see this graph, previously it just learned at this position, but now it just after it learns better at the like, 19.1. We can, all the code and everything is just same as before. And this is okay. So this is taking some different route here. The outputs and everything is just the same, like evaluations, and this is the like, different, more flexibles as I talked before. And it's like, SNG instead of that one. And the steep QN, which we are going to see in the very brief, there is mainly 3 steps. We know this one, choosing action using epsilon greedy strategy. And then we update the new network. So it's like, neural network kind of architectures. So updates the weight using the Bellman equation. It could be some another two. So yeah, so this is all the like 3 steps. And then you have kind of the neural network kind of thing. We can't go into this one because we are kind of short of the time, but this is a pretty simple case where how you can implement the DQ. And I also attached to this link to which you can of course access. And let's see the real life examples. So games, we've seen that a lot, and reinforcement learning is a lot used in the NLP side of NLP areas too. So for example, this screenshot I basically taken from the OpenAI's official GPT-3 where they published and everything. So it actually, this lines clearly state to make the model refer more helpful. They are using the extracting reinforcement learning from the human feedback. So it learns from the human interactions. And they saw the GPT-3, and GPT-3 is of course used in summarizations and lots of other tasks where the human like, so say like it prompts like, whether it's good or not. And the autonomous driving, actually Amazon has a pretty good tutorial for that one, for those folks who are interested in building the such kind of car. It gives environment, as we've seen with the gym, and you can also train with the SageMaker and all the resources at the AWS simulator car. And then like if your algorithm is good, or like winning with the kind of competition they have. So it's also great. Then recommendation, as we see in the Netflix or YouTube, based on whatever our activity, we got the suggestions in that one. In the trading and finance, like in the trading, there are like mainly 3 actions here: buy, sell, or hold. We have seen like, time series wise, where we predict the stocks and all based on past data, but here is about the taking action, whether you should buy right now, sell, or like hold it. So that's how the like environment is, like in all the stock markets and trading and everything, and rewards in this case is our profit that we got. And the industrial automations, like robots and everything, as we've seen before. So it's like, automating a lots of things. And this is the last slide, which is the reinforcement learning resources. So these books, so categorized by books, lecture courses and the tutorials, and open source repo as well. If you are learning more in like, practical examples. So this is like godfather of the reinforcement learning from the Richard Sutton. Ebook is its second version. So there's like lots of theory concepts and lots of new algorithms they have provided. And this is lecture. I've actually liked this a lot. UC Berkeley's this lecture, they have the videos. Yeah, so here they have the videos and also some materials too. And the second one, which is around the Coursera's reinforcement learning specialization, as we have for the ML, so it's same for the reinforcement learning. And this is pretty quick, like, 3 where if you want to learn the reinforcement learning, then this guy's tutorial is also, I think, helpful. This one is also good, reinforcement learning by the David Silver. So you got the slides, lecture notes, and everything actually. So like, lecture by is lecture, it gives the explanation and everything. So yeah, in open source repository and everything. So yeah, that was me, Krupa Galiya. So I wish you all the best and keep learning, exploring and learning RL agents, because we are also reinforcement learners. Cool, thank you so much. Any reason running Google Colab more horsepower, GPU, TPU requirement? So as I mentioned, right now we are not using GPU or TPU, but here we are using Google Colab, so I can easily share my code, and you can also do the like, coding with me on the live too. And it will be same environment, so we will not have like, requirement kind of thing, like I'm getting some error in some requirements or dependencies thing. So that's why I just have same one, and it's easy to share. So that's why we are using the Google Colab. Okay. And there was one question about which policy have you find the smartest so far? So I can say like, DQN is the most popular when you have the complex like a 2D or 3D kind of problems. For DQN, it works like, as we have the neural network, so it's kind of same. So in that one, it actually able to solve the pretty complex problem. But when we have such like, smaller kind of problem, then in this case, Q learning is the best one to go with, as we have also the example we have taken. So in that one, Q learning was performing the exact well.